Absorption spectrum. When relatively cold, low-density gas vapor is placed between a hot light source and the observer, the gas vapor absorbs some of the photons that pass through, producing an absorption spectrum. The situation is just like this diagram at the top. There is a source that produces a continuous spectrum, and then there is low-density gas such as hydrogen in between the light source and the observer on the other side. And now, when light passes through the hydrogen gas, the electron is promoted to higher energy state when a UV is absorbed. Later on, when it returns to lower energy level, UV light is emitted in all directions. Let's try other settings. We do that again. And now, the photon is absorbed, and this time is also a UV light. And the UV light is re-emitted in another direction, so that the forward direction has less photons of this frequency. The absorbed photons excite the atoms, and these atoms radiate EM waves to all directions randomly, so that the intensity of their characteristic frequencies become lower and appear as dark lines in the spectrum, and sometimes even through multiple transitions to lower energy levels by emitting multiple photons. For both emission and absorption, we can calculate the wavelength of corresponding EM radiation using the equation here listed on page 64. The formula was first identified as Ribot's formula, where the Ribot's constant was determined experimentally. It was only after many years of the study of atomic physics that scientists eventually explained the value of Ribot's constant. Refer to the supplementary information on page 65 for the earliest study of spectral lines. Example 5. Re-emission from an excited atom. In this question, there are 3 energy states. When the electron at the ground state is excited to the second excited state, there can be 3 possible transitions. Which are they? Now refer to part B, please. So, which transition has a higher possibility? No one knows. But if you refer to the emission line spectrum and find that the corresponding line is brighter, then you may say there are more photons of that particular energy. Remember, in the Let's Begin section, we mentioned flame test. Different colors of flame is due to different sets of energy levels in different atoms. Exam link 1. Color of spectral lines. While the energy levels may not be drawn in scale, the lengths of arrow that represent the electron transition can still give a clue to the size of energy of photon. To compare the energy and frequency of photon more accurately, you have to apply the formula to calculate the energy difference between levels. When these transitions emit photons, these photons will produce a line spectrum like this. Exam link 2. Spectrum and energy levels. In part A, you are asked to give evidence for discrete energy levels. You should always remember line spectrum is the only sound evidence. And for part B, it should be quite straightforward. Four, limitations of Bohr's model. Although Bohr's model successfully states conditions of stable electron orbits of hydrogen atom and then explains spectral lines due to electron transitions, it does not explain the relative brightness of spectral lines, the spectra of other atoms, the fine structure of spectral lines, and the reason why the angular momentum should be an integral multiple of h over 2 pi. Do check point 5 on the next page.